There are four main pillars of modern mathematics, and if you want to learn any of those four pillars, in order to understand what is actually going on, you're going to need to understand set theory. And set theory forms the backbone of algebra if you want to learn algebra, geometry if you want to learn geometry, analysis if you want to learn analysis, or topology if you want to learn topology. Resize me, baby. Thank you. Let's begin our discussion of set theory by first asking the question, what actually is a set? Well, by definition, a set is an unordered collection of unique objects, which might sound scary at first until you realize that you've been using it in your everyday language like your whole life. And you could just think of it as, say, I had the set of tables in my apartment. So, for example, I have 3 tables in my apartment. The desk that I'm currently on, so the desk that I am currently on, I have a coffee table in my apartment, and I have a kitchen table in my apartment. And this is an unordered collection of unique objects because each of these objects only appears once within our set. The collection has no order. There is no first table. Either the table is inside of our collection of objects or not inside of our collection of objects. And that's about it, actually. Now you could see that a set is denoted by curly braces. So a curly bracket denotes that you are inside of a set, and all of the members of a set are separated by commas. Another example that my mother particularly likes because she's a big football fan is the set of all football teams. So in our household, we are Jets fans, but we have Jets, we have the Giants, we have the Bills, we have the fucking Patriots, those pieces of shit, and there are 28 other football teams. Now, fundamentally, the thing about sets is that the fact that we can write this set out doesn't really matter. What's very important is if I was to pick any particular item and ask you whether or not it was inside of our set, you should be able to answer the question yes or no. So if we call our set of NFL football teams F, we should be able to ask the question, given some particular item, is that item inside of F? Are the Jets inside of the set of NFL football teams? Where this notation right here means inside. So this is a symbol to say set membership. It is in the set. Well, the answer would be yes, because this is, in fact, inside of the set of football teams. The Jets are a football team, even if a dog shit one. If I was to say, are the New York Mets inside the set of NFL football teams? Well, the answer would be no, because the Mets are actually a baseball team. So no, the Mets are not inside the set of football teams, and we would denote this by saying the Mets are not inside of it. So you put a little slash through our set membership operator. Traditionally, though, we think of sets in terms of numbers because this is a math class that we're going to be talking about. So if I was to say that our set A was the set 1, 2, 3, 4, and 5, we could say something like 1 is in fact a member of the set A, 2 is in fact a member of the set A, but the number 6 is not in fact a member of the set A. An exercise that I would give to you, should you want to write it down, is to write out the set of members in your family. So set of family members. This will be unique to you. For myself, I have a father, a mother, and a sister. Now that we have sets, sometimes we can even relate sets together. So suppose I have a set A, which from before we said is the set 1, 2, 3, 4, 5. And for example, let's just say I have the set B, which is equal to 1, 2. Now we see that there exists some items inside of A that are not present in B. For example, 3 is in fact in A. However, 3 is not in fact inside B. Yet, if we were to look at every single item that is inside B, every item inside of B is inside of A. Now, this is quite special. And in fact, we have a term for this. If all items in B are inside A, then B is a subset of A. Specifically notated as B is a subset of A, where this means subset or equal to. The little line on the bottom means that it actually can be equal, so it is actually possible for B to be equal to A, in the same way that we might say that x is less than or equal to y if we were talking about two numbers. And it is also, as we see, that b in fact is not equal to a. So if we know for a fact that b is a subset of a, but b is not equal to a, we often will write it as b is a proper subset of a, which means b is a subset of a, but b is not equal to a. There must exist some item inside of a that is not in b, or just x is less than y instead of x is less than or equal to y. But wait a second, what does it mean for two sets to be equal? We've just talked about what a set even is. It's just a collection of items, and we said that one set could be a subset of another set if all of the items inside of one set are inside of the other one. So what does it mean for two sets to be equal? We haven't actually talked about something like that yet. We actually take this by assumption. This is in fact considered an axiom of mathematics, which if you don't know what an axiom is, it's a statement that we actually can't prove. We take it as an assumption to form a foundation of our mathematics building blocks. Now, axioms should be particularly obvious, and this one, which is called the axiom of extensionality, actually is pretty freaking obvious. And it says that two sets, A and B, are equal if and only if they contain the same items. We say the axiom of extensionality tells us that two sets are equal if and only if they contain the same items. Now, you might be thinking, well, yeah, no shit, Joe, like, duh. Obviously, if the two sets have the same items, then they must be the same set. That is why we take it as an axiom, because it feels very obvious, it feels very natural and intuitive. We shouldn't have to prove it. We could just take this on assumption. For example, I would have the set 1, 2, 3 is in fact equal to the set 1, 2, 3. Okay, is 1 inside of this set over here? Yes. Is 2 inside of this set over here? Yes. Is 3 inside of this set over here? Yes. And then you could do the same process the other way. Is 1 in here? Yes. 2 in here? Yes. 3 in here? Yes. But writing out sets in this way, like just writing out every single potential item, is going to get really, really tiring really, really fast. For example, say I wanted the set of all even numbers, which I usually write like this. The set of all even numbers, that's 0, 2, 4, 6, 8, 10, ... In fact, there's an infinite number of them. I'll never be able to write every single even number. What we need is we need a nice, convenient shorthand way of writing sets for us. And the way we are going to do that is by using something called set builder notation. This is notation that helps us build sets. For an easy example, let's build the set of all numbers that are between 0 and 10. Let's say that our set A is equal to the set of all values x, such that x is a real number and 0 is less than or equal to x, which is less than or equal to 10. And this will give us the set of all numbers that are between 0 and 10. So what is this doing? This is saying, well, okay, build us a set of all values. These are the values that we are plugging into our set. So values in our set. This bar separates and means such that x satisfies this condition. So satisfies this condition. Again, we're looking for the set of all values x, and remember that whatever is on the left side of this bar here is whatever we're plugging in. So we can actually perform operations on this left side. We can modify x in whatever way we see fit. Whatever happens on this side gets plugged into our set, whereas whatever is on this right side here is the condition that x needs to satisfy in order to be actually used and plugged into our set on the other side. Now note is that I actually had to specify what type of value x actually was. I couldn't just say, let x be a number between 0 and 10, plug it in, because then it's kind of ambiguous. Are we talking about real numbers? Can it be fractions? Does it have to be whole numbers? As such, we need to specify the universe that we are working inside of. Just know that in the event that you don't specify your universe, or you don't think you need to, some very, very bad fucking things can happen to you. In fact, let's list off some of these important sets that we're going to be seeing a lot of whenever we're doing any sort of mathematics. Probably the most important of every set you could ever imagine is the empty set. This is the set that contains nothing. After the empty set, we have the natural numbers, which are the whole numbers that start at 0. So 0, 1, 2, 3, ... This is a contentious subject, actually, depending on who you ask, whether this starts at 0 or 1. However, I will start at 0 because it makes some things much, much cleaner. Next, we have the integers, which is represented by z for some reason, which is all the whole numbers, either positive or negative. So negative infinity all the way off, -1, 0, 1, 2, ... Next, we have the rational numbers, which contains not just the whole numbers, so 0, 1, -1, -5, for example, but it also contains all positive and negative fractions. So 1/2, -2/3, yada, 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 etc., etc. We also have the real numbers, which is the biggest Mac Daddy of all the sets. It contains all the whole numbers, so 0, 1, -1, all the fractions too, negative fractions, and it contains both rational and irrational numbers. So we get things like pi, -pi, square root of 2, all the way off to infinity. As a brief aside, in the event that we wanted the whole numbers starting at 1, so we wanted the set of all whole numbers from 1 to infinity, not including 0, I will often notate this as z_plus, or specifically called the positive integers. Let's close out this episode with a problem that brings all of the concepts that we've talked about together, and in terms of difficulty, I will label this as a level 70 problem in the event that you have not seen any of these concepts before ever. For this problem, I'm going to define two sets. S1 equal to the set of all values x squared, such that x is, in fact, a natural number. So remember, natural numbers are whole numbers starting at 0, and I'm going to create the set S2, which is equal to the set of all values x squared, such that x is an integer. So this is all whole numbers that are both positive and negative. S1 is going to look like both 0 squared, 1 squared, 2 squared, all the way off to infinity. And S2 is going to be equal to 0 squared, 1 squared, -1 squared, 2 squared, -2 squared. The question and the problem being asked is S1 equal to S2? Are these two sets, in fact, the same set? Pause the video, try to think about it, and come up with the solution. The answer to this question is, in fact, yes. These two sets are the same set. So remember that, one, a set only cares about unique elements. So we do not keep track of copies inside of the set, as 1 squared is equal to 1, and negative squared is also equal to 1. 2 squared is 4, -2 squared is also equal to 4. So the fact that we have the same value repeated multiple times, we don't care about that. All we care about is 1 squared, or is the number 1 a member of our set? Yes. Is 4 a member of our set? Yes. Remember, all we care about sets is either whether the element is inside or not inside of the set. We don't keep track of the number of times you plug it in. It's either in or not inside. Using the axiom of extensionality, all we need to know is every item inside of S1 inside of S2 and vice versa. Well, is 0 squared inside of S2? Yes. Is 1 squared inside of S2? Yes. Is 2 squared inside of S2? Yes. And by vice versa, you could say the same exact thing. -1 squared is just 1. Since -1 squared is just 1, we don't keep track of it. S1 and S2, therefore, must be equal to each other. QED.